Hello, everyone. Welcome to AI4. Our next session is going to be led by Chris Milligan. He is a Factory 4.0 coordinator at Nissan. Please join me in giving Chris a great virtual welcome as he turns on his video and turns on his screen sharing.
Thank you.
Thank you so much, Chris. Take it away.
Well, good afternoon, everyone. As Patricia said, my name is Chris Milligan. I am a senior manager for Nissan's powertrain facility in Decker, Tennessee, and the Factory 4.0 coordinator. I'll get started. When I first started my machine learning journey, I was frustrated because all the books talked about predicting people, basically. There was an abundance of applications in fintech, customer acquisition, retention, and management, but very few applications in manufacturing besides a few use cases in preventive maintenance. There are some startups trying to apply the same tools made for these kinds of problems, but they're not always the best fit, and they're also very high risk. As you are probably aware, the majority of data science projects never make it into production. In industries where there's a high profit margin, if it's successful, these things, we can kind of afford these gambles. But in lean manufacturing, we need a different approach because really we do have a very low profit margin. So when I speak to my peers in manufacturing space, there's a lot of frustration over advancements in general. Automation has been the driving force behind manufacturing's ability to keep prices low, despite rising cost of labor and materials. However, when you talk to the teams running manufacturing plants, automation is practically derided. This may be why a number of robots per capita in the US is lagging several other advanced industrialized nations, such as South Korea, Japan, and Germany. But why is that? Understanding this problem is important because it will be an even greater drag on our ability to implement artificial intelligence, partly because of the negative public perception of the technology itself. So to understand this, what I believe to be the cause, we need to ask ourselves, what is the purpose of your manufacturing teams? Unless a manufacturing employee is actively producing the product being made, they're essentially problem solvers. Your managers, engineers, and technologists are day in and day out looking for ways to improve efficiency and resource usage while overcoming equipment and quality issues. So if your team isn't excited about implementation of automation, especially in its new form, AI, it may be because they are perceiving it as an increase in the number of problems they will have to solve and manage. Since many of them don't understand the underlying mathematics and principles behind how it works, they can't even imagine being able to solve the problems generated from these technologies. This is issue number one we need to address. Issue number two has to do with the technology itself. American culture is not all that comfortable with the concepts of machines that can make decisions, which is essentially the purpose of the field. For example, one survey found that half of Americans say they will never utilize an autonomous vehicle. If it's true, it's going to make the transition to transportation as a service a little bit difficult, but there will still be a market for the other 52%. However, if half of your manufacturing team is equally as resistant to autonomous technologies in your plant, you will have a significant implementation problem. So what do we do about this? The answer to this problem lies in how automation in the vehicle itself has been developed. This has largely been an incremental buildup of trust and confidence. It starts with simple things like cruise control. The user selects the desired speed, and it's easy to disable by instinctively touching the brake pedal. Then we add other alerts like blind spot warning, automated lights, and windshield wipers, all of which leaves the driver still in complete control of the vehicle. Then we add our first superhuman technology with emergency braking. This teaches us that the technology has our back when we let our guard down. Now we have shown the driver that the technology is capable of taking control to protect us. These advances lead to further control of the vehicle, such as intelligent cruise control, 360-degree safety protection, such as lane assist, and finally stepping towards autonomy with vehicles maintaining themselves in their lane. For us, even doing some parallel parking for us, which I'm terrible at personally. Each step along the way, we have built trust in our technology, and just as most people are willing to fly today, thanks to the impeccable safety records of our airlines, we will also reach full adoption of autonomous vehicles in this manner as well, because it will be safer than you driving it yourself. So my proposition is that we leverage this same strategy to help our AI skeptics adopt the smart factory. So if we keep these two concepts in mind, that we need to keep help our teams become more comfortable with AI through a scaled introduction, and that we need to be solving their problems first, I believe we can be much more successful in being able to take advantage of this breakthrough quickly. I'd like to take you on a journey that begins with the simplest examples of how we can use data science and machine learning techniques to solve our problems, all the way up to the cutting edge of AI for advanced automation. First, we're going to take a look at what AI can do with the data that we probably already have in place and readily available. There are approximately 2,000 moving parts in a vehicle, and they now, thanks to globalization, come from factories all around the world, and in turn are supplied by other factories. And each is going through its own evolution to try to stay ahead of cost pressures by innovating new ways to run the business. Because of this, the final assembly of engines and vehicles is a continuous battle to stay ahead of the changing supply of parts. As a result, the most common question asked when a new problem occurs is what changed? This is how we start our troubleshooting process. Most of us are already collecting some form of quality traceability data. Many times when a new problem happens, engineers go through this data for a change point, either to understand the root cause of the new problem or to find the beginning of a window for the problem. In many cases, statistical process control software are not as useful for controlling these kind of issues, because of what makes a good and bad part is largely due to combination with another part or feature. You may also notice that these examples, that there are lots of outliers in this kind of data, which can be quite common, even though they don't really affect the final part quality. The same concept follows from predictive maintenance. Many failures have some degradation, which can be measured and detected with an increasing rate of decay as the failure approaches. If detected early enough, these failures may be corrected at a lower cost to the facility. Several techniques exist to identify changes in a data set. A simple one that I would like to highlight here is Bayesian change point detection, as it can detect changes in mean, variance, and distribution of the data from normal. The advantage of this technique is that it's largely immune to those outliers and doesn't require a historical data set, which means ROI from incorporating this technique can be fast and doesn't require collecting and labeling a lot of data. So just to show how sensitive this technique can be, I've created some simulated data sets to show it detecting at first. This is an example of a mean shift. You can just kind of barely see it making that little step change, and it detects that successfully. Here's an increase in variance. So the overall data spread gets a little bit wider in that case. And this last example is a change from a normal distribution to a different kind of distribution called a gamma distribution, and it's a little bit skewed. And in all cases, the technique captures it very early on. In some cases, the data being measured has a very low signal to noise ratio, such that it can be a lot like looking for a needle in a haystack. And in some cases, machine learning can be used to greatly reduce that noise. To avoid confusion, I'm going to use an example from investing to explain what I mean here, so that it's more intuitive for everybody. So everyone knows if you have the most basic of education investing, you know that you need to diversify your investments. The reason for this is that you put a lot of your investment in one asset class. All those investments tend to move together, or in statisticians' terms, they correlate. So I have here the history of stocks for several oil companies. And let's imagine that we think that one of these companies, Valero, the blue bar, is a good investment, possibly. So we want to watch it to see if it breaks out from its peers. So what we're going to do here is we're going to take the other oil companies, and we're going to try to predict what Valero's stock price should be. And that's the middle here. The orange is the prediction, and the blue is the actual on the central graph. But we're not really interested in the prediction. We're actually interested in the error between the two. And that's what this red line is. It's the error between the prediction and the actual. And that error is what we're going to monitor, because that error will tell us if the correlation starts to break down or diverges. So a year later, we've got new data, and you can see we've run up to a peak and we've started falling back down to sort of a regression to the mean. And our model still is good as far as the prediction error. But then one more year later, they start to diverge. And this divergence is what we're going to look for in our data set. And that's what's going to tell us something is going on with this data. In the case of Valerio, just by chance, my hypothetical example here, the hunch turns out to be true, and Valerio's price takes off relative to its peers. Now, this is just an illustration that I've made to help us understand how this process works, but I do have over 500 models running every night on IoT data, applying this technique to look for the sensors themselves to have failed. And it keeps coming up in new applications for me, so I keep finding new ways to apply it. So I think of this as a sort of automated blind spot warning system. Since we now have a mechanism and a reason to collect a lot of this data and store it for our products and our equipment, what else might we do with it? Well, one of the things about manufacturing processes is that they have several hundreds of specifications, and engineers and technicians spend hours every week trying to prevent these various features from drifting out of spec. It is also a tremendous engineering challenge to design products with specs that meet the balance between financially efficient manufacturing on one side and high quality products on the other. Since tolerances and specifications between features can kind of stack up, which means if this one is at one end of its spec and that one's at the other end of its spec, it can actually become a problem. And diagnosing these problems are very difficult, and they're also inevitable eventually. So the problems typically manifest when, like I said, when these multiple features kind of work together. The stack up problem can be compounded further when some of your processes are running through parallel assets. So you have the same machine doing the same process, and they diverge and come back together eventually. Fortunately, traceability is a growing movement in supply chains thanks to RFID and various 2D codes, which can be placed directly on the part. This provides a means of creating a sort of digital fingerprint. With this data, it may be possible to identify problems with those specification stack-ups and create a sort of digital quality monitoring system. We're actually investigating this now. As our teams gain understanding and trust using these automated processes to monitor our data, we can then start having it give feedback to earlier processes to make adjustments. Initially, this can just provide recommendations to the workers to help them identify how much a change to make. But once the trust is in place, autonomous feedback can be added to keep the dimensions at their nominal readings at all times, greatly improving our quality and eliminating those stack-up issues. As an example of this, here's something that my team is working on. Currently, one of our grinding machines is producing crankshafts, but the measuring station that validates the part is several stations down the line. Over time, these machines drift enough that technicians must make adjustments to the machine, which can be a difficult process of running a part, testing it, rerunning the next part, making another change to make sure the move is as expected. And each time we must wait for that part to get down to the end of the line to validate our change. So we built a machine learning model that uses the axis position data and sensor readings in the grinding machine itself to predict what the gauge is going to read when the part reaches it. We're now moving to put this on the edge, on an edge computing device, to use the model to continuously feed back to the machine with those necessary offsets. The model itself can then be validated by feedback from the gauge data to ensure that everything continues to stay in the center of the spec, which eliminates the drift problem altogether, and the need for the technician to interface with the machine. One of the biggest breakthroughs in AI and machine learning is in deep learning based vision. This tech is at the center of powering autonomous vehicles, cancer detection, facial recognition, and now manufacturing quality. Many defects in manufacturing are best detected via visual inspection. As a result, people are inspecting products as they traverse virtually every production line in the world. The problem is that we human beings are quite fallible and tend to miss some defects, especially new types of defects and ones that are a little bit more subtle. Deep learning-based vision systems can provide better quality detection than the person it replaces, while simultaneously providing a financial savings for us. Since we began installing these systems, they have caught things for us that are virtually impossible for the average person to detect. And when they do detect something, the system shows the user exactly where the problem is so they can confirm it for themselves. You might know that traditional rule-based vision systems are already in place all over our factories. These cameras perform admirably in simple applications where consistency is sufficient, but as soon as there is variance in the part or the lighting, they become problematic. Since AI vision systems learn what to look for automatically from the part data itself, they are much more tolerant of this variance, all without requiring complex rules and tuning of the system by experts. And if the part changes, the system can quickly be retrained with the new data. The AI systems are also capable of a few things that traditional vision systems are not capable of, such as visual anomaly detection. So if you didn't teach it what to look for, it just knows that something has changed. It can actually call those out, as well as some very difficult character recognition that can't be picked up by traditional cameras. If you haven't been in one of America's many automotive factories, you might think of them as what you see in the commercial, lots of robots assembling cars. The reality is, much of the final assembly is still performed by people. Outside of social media and e-commerce, people are not the best data generators. So data on production processes are still gathered with stopwatches, pen and paper by industrial engineers, and the process itself is validated via supervisor job observations. What if AI could help us with that? In fact, it can, thanks to deep learning combined with continuous video feeds to the cloud for processing. We're testing one company on this opportunity. What can be done with video monitoring is continuous job observations that, given detailed statistics on the process broken down into individual cycle times, that provide engineers with a distribution of those times rather than just a few summary statistics. Beyond that, poke-yokes or error proofing can be put in place to flag activities that are performed out of process. With something like this in place, manufacturers can try new things without the risk of out-of-process errors, one of the most common causes of defects. So now that we've put in place some technology to make our jobs easier and our quality and efficiency better, we can think about adding new automation. This is where AI is going to make the biggest financial impact in the coming years. Robotics, as you may know, has been a main branch of the discipline since its inception in the 1950s. But we don't have to wait for evolution of robotics to advance to something humanoid to start taking advantage of it either. In fact, many breakthroughs are applicable today that do not even require drastic changes from technology that's already being applied in the industry. For example, automated guided vehicles or carts have been used in the industry for decades already, and AI can make this workhorse more valuable to us. Over the useful life of a vehicle, there are 4 major cost categories. A more intelligent vehicle can lower all these costs. Rule-based software requires a lot of effort to program, which increases the cost of the vehicle itself. It also increases the cost and risk when it comes to engineering and integration because each job requires analysis, simulation, and planning for all the special cases that may occur. I've recently been talking with other plants before purchasing new equipment, and some manufacturers have robotic graveyards due to the projects that failed to perform as originally specified, or some unforeseen problem caused them to cost more than the price of paying people to do the work itself. Even if it does work, the lack of flexibility means that the OEM must be called back at a great expense to make any changes to the path. Since some manufacturers pay to get their employees trained to do this, but they don't do it often enough for the skills to be persistent. On the operation side, because these vehicles don't know how to adapt to a changing environment, they frequently cause operational issues that human drivers would not have a problem with, such as stopping due to a piece of trash being in their path, or blocking a lane due to a machine that it's feeding being down. If you've been following the development of autonomous vehicles on our roadways, you know it is a hard problem, but it has been making some amazing breakthroughs. And by contrast, factories are not nearly as varied or complicated as our road systems. And LiDAR safety systems and slow movement speeds means that safety concerns can basically be completely accounted for compared to automobiles. Several startups are now making autonomous vehicles based on this technology for our factories. Those autonomous vehicles have the advantage of being able to see the world around them and can adapt when that world changes without having to be specifically programmed to do so. This means issues like misalignment or obstacles in the normal route are handled automatically via recalculation updates, just like your GPS does when you deviate from the route that you have programmed in it. These vehicles don't require infrastructure either, such as tape or reflectors or devices embedded in the floor for their guidance, which means that they can flexibly move about jobs rather than being stuck to specific routes. This lowers the total number of vehicles required. It limits operational downtime because a downed vehicle can automatically be replaced by another that's on the line ready to go, and just a new job be called up. It also virtually eliminates the engineering cost of making changes because in-house teams can add new work assignments easily. Moreover, there is a second wave of advantage when software that controls the fleet is considered. Vehicles are running a mess of routes across our factories. Because of these routes are set up so that vehicle operators don't have to make too many decisions, there isn't an opportunity to achieve efficiencies if the path planning and job sequences were optimized using predictive analytics to identify the next load is needed rather than waiting for the job requirement. So finally, let's talk about robots. Specifically, these new collaborative robots that have been making waves in numerous industries in retail, hospitality, and research at academia. Since robots have been used in the automotive industry for decades, these new cobots haven't really made quite the same impact as they could if a little AI were added. Recent developments and ongoing research may change that very soon. Being able to see complex objects with depth perception and being able to classify objects and orient them so that the robot can work in these complex environments that were previously impossible. Building on these ideas, we can add collision avoidance. Currently, the speeds on collaborative robots needs to be slow enough so that only minor bruising occurs should said collision happen. If this can work well enough to allow cars to safely travel on public roads, it should allow cobots to run at higher speeds and even interact directly with the workers around them. This also means that working environment can be much more dynamic and flexible, something that robots typically could not tolerate. After giving robots the ability to see, the next thing is to provide them the ability to feel. Force feedback means that robots can assemble things that require careful alignment. With a search feature, even tight fits and easily damaged components can be assembled. If we take the ability to see and feel together, robots can assemble just about anything. And research has even begun to create robots that can assemble things without being programmed specifically to do so. What I imagine the last frontier in this space to be is the mimicking of the human hand, specifically our dexterity. Servo controls and force feedback can make the controls very finely tunable, but imagine trying to program a device like this servo-driven robotic hand. That would be a very complex task to do ourselves. However, researchers at OpenAI have started showing the way through their simulation processes that leverages evolutionary algorithms to allow virtual hands to emerge. This is still very much a young research activity, but the early results are exciting and promising, with hands even being able to manipulate Rubik's Cubes, one hand by itself. The hard part is getting these machines to the point where they can do things that we find natural and easy. Once that is figured out, though, the computational power allows them to solve things that are not so easy for us because, honestly, quickly moving to superhuman capabilities, such as this two-jointed inverted pendulum. This device was self-learned how to balance, even though it has joints twice in its middle, something that we can't possibly do. If these things are achieved, full automation may be possible. But just in case it is, we should start thinking today about what that means for us as a society in the not too distant future. Thank you for coming to my presentation. If you would like to connect with me afterwards, you can find me on LinkedIn with the image here. Thank you again for coming, and hopefully we can have some questions.
Awesome. Thank you so much, Chris, for that super insightful presentation. We're really excited that you were able to join us today, and a big virtual round of applause from the audience. Yay! All right, everyone, please feel free to find your next session on the agenda, and we will be offering networking opportunities as well. So take a look at those, and we'll see you around. Thank you.